Iceland is being torn in two. This is not a metaphor or an exaggeration, but a verifiable geological process monitored in real time with instruments capable of millimeter precision. Recent data has significantly reshaped how scientists understand this landmass in the middle of the North Atlantic. How fast can a country physically split before its infrastructure begins to feel the strain? What happens when the ground beneath homes, roads, and power systems is not stable, but steadily diverging? And how long can such a process accelerate before its impacts extend far beyond national borders? Two of the largest tectonic plates on Earth are actively separating beneath Iceland, pushing the crust in opposite directions with immense force. Analysis of GPS data published by the Icelandic Meteorological Office and multiple European research institutions reveals a pattern that is not static but dynamic, with measurable fluctuations in both speed and intensity. The North American plate is drifting westward, while the Eurasian plate is moving eastward, creating a widening fracture zone that cuts directly across the island. This movement is not theoretical. It is recorded continuously through dense geodetic networks that measure displacement down to fractions of a millimeter. Under typical conditions, the rate of separation averages roughly 3/4 of an inch per year, or approximately 18 to 19 millimeters annually, approaching nearly 2 centimeters. Over a span of 10 years, this results in a displacement of about 8 inches or 20 centimeters between two fixed points located on opposite sides of the rift. However, recent observations indicate that this baseline rate is not constant. During periods of heightened tectonic and volcanic activity, the rate can accelerate significantly, at times exceeding more than 1 inch per year or over 30 millimeters annually. These surges are not gradual. They occur in pulses tied to subsurface magma movement and crustal fracturing. Iceland occupies a singular geological position. It is the only location on Earth where the mid-Atlantic ridge emerges above sea level, providing direct access to a process that typically unfolds thousands of meters beneath the ocean surface. This exposure allows scientists to observe plate tectonics in a way that is otherwise impossible, but it also means that the consequences of these movements are experienced directly by the population. Roads deform, pipelines shift, and entire sections of land can become unstable over relatively short periods. The separation does not occur evenly across the island. Instead, it is concentrated along rift zones, the most active of which currently lies on the Reykjanes Peninsula in southwestern Iceland. This region has become the focal point of intensified geological activity since 2021, marking the end of an approximately 800-year period of relative dormancy. Since that time, a sequence of 12 eruptions has been recorded through 2025, with 9 clustered within the Sundanukur volcanic system beginning in mid-December 2023. This cluster of activity represents a shift in behavior. Historically, eruptions in Iceland have been distributed across multiple volcanic systems with varying intervals between events. The current pattern, by contrast, shows repeated eruptions originating from closely spaced fissures over a compressed time frame. Each event follows a similar sequence. Magma accumulates beneath the surface, the ground begins to rise, seismic activity increases, and eventually the crust fractures, allowing molten rock to reach the surface. Measurements indicate that prior to each eruption, between approximately 17 million and 23 million cubic meters of magma accumulate beneath the Svartsengi region, at depths ranging from roughly 1.5 miles to 2.5 miles, or about 2.5 to 4 kilometers. This volume is substantial. At the upper end, it is equivalent to roughly 8,000 Olympic-sized swimming pools filled with molten rock concentrated in a confined subsurface reservoir. The pressure generated by such accumulation exerts force on the surrounding crust, leading to measurable ground deformation. Satellite radar and ground-based GPS systems detect these changes with high precision. Uplift of several inches or multiple centimeters over a matter of weeks indicates that magma is building beneath the surface. When an eruption occurs This uplift is rapidly replaced by subsidence as the magma either escapes or redistributes within the crust. This cycle has repeated multiple times in rapid succession, suggesting a sustained supply of magma feeding the system. Beneath Iceland lies a mantle plume, a column of abnormally hot rock rising from deep within the Earth's mantle. This plume provides a continuous source of magma that interacts with the separating tectonic plates above. The combination of plate divergence and plume activity creates a geological environment characterized by both extension and upwelling, a dual mechanism that intensifies volcanic output and accelerates crustal deformation. In most parts of the world, these processes occur independently. In Iceland, they are superimposed, amplifying each other. The Reykjanes Peninsula illustrates this interaction with unusual clarity. As the plates pull apart, fractures develop in the crust, forming pathways known as dikes. These dikes can extend for several miles or multiple kilometers, horizontally and vertically, injecting magma into new areas of the crust. Not all dikes result in eruptions. Some stall underground, redistributing stress without reaching the surface. Others propagate rapidly, breaking through and producing fissure eruptions that can stretch for hundreds of meters, sometimes exceeding half a mile in length. A detailed analysis conducted over a 12-month period between late 2023 and late 2024 identified 9 distinct dike intrusion events within a monitored corridor approximately 62 miles long, or 100 kilometers. Of these 9 intrusions, 6 led to surface eruptions, while 3 remained contained below ground. This variability highlights a critical uncertainty. While scientists can detect magma movement with increasing accuracy, predicting whether an intrusion will culminate in an eruption remains an unresolved challenge. Each intrusion event alters the stress field of the surrounding crust. When magma forces its way into a fracture, it pushes the rock apart, effectively widening the rift. This process contributes directly to the overall separation of the tectonic plates. In other words, volcanic activity is not merely a byproduct of plate movement, it is an active driver of that movement. The more magma intrudes and erupts, the faster the crust can be forced apart in localized regions. The effects of this process are not confined to remote or uninhabited areas. The town of Grindavik, located near the center of recent activity, has experienced repeated evacuations due to ground deformation and volcanic hazards. Cracks have opened in streets and residential zones, in some cases extending for several hundred feet or over 100 meters. Infrastructure has been damaged, including water lines and electrical systems, requiring rapid response measures to maintain essential services. Air quality has also been affected. Eruptions release sulfur dioxide, a gas that can pose health risks when concentrations rise. During active periods, gas plumes have drifted across populated areas, prompting advisories and temporary closures. While these emissions are typically short-lived, their recurrence over a condensed time frame increases cumulative exposure. The implications extend beyond Iceland's borders. Volcanic ash and gas emissions can disrupt air travel, as demonstrated in 2010 when an eruption at Eyjafjallajökull led to widespread flight cancellations across Europe. That event resulted in the closure of large portions of European airspace for nearly 1 week, affecting millions of passengers and causing significant economic losses. Although recent eruptions on the Reykjanes Peninsula have not produced ash clouds of comparable scale, the potential for such disruptions remains present, particularly if eruption dynamics shift. There is also a broader atmospheric dimension to consider. Volcanic gases, including sulfur dioxide, can influence climate by forming aerosols that reflect sunlight. Large-scale eruptions have historically produced measurable cooling effects. While the current eruptions in Iceland are relatively modest compared to major global events, their frequency introduces a cumulative factor that is being closely monitored. Recent data indicates that by late November 2025, Magma accumulation beneath Svartsengi had once again approached approximately 20 million cubic meters, nearing the upper threshold observed before previous eruptions. Ground deformation patterns suggest that pressure is rebuilding, following the same sequence observed prior to earlier events in the cycle. The repetition of this pattern raises a critical operational question. How many cycles can occur in succession before the system undergoes a more significant change in behavior? The rate of plate separation, the supply of magma from the mantle plume, and the mechanical properties of the crust all interact in a complex system that is still being mapped in detail. What is clear from current observations is that the process is ongoing, measurable, and evolving. The rift is not static, it is actively expanding, with periods of acceleration that exceed historical baselines. Across the Reykjanes Peninsula, new lava fields have formed where none existed just a few years ago. These fields cover areas measured in square miles and square kilometers, reshaping the landscape and altering drainage patterns. In some cases, lava flows have approached critical infrastructure, requiring the construction of defensive barriers to redirect molten rock away from key facilities. The monitoring systems deployed across Iceland represent one of the most advanced geophysical networks in the world. Continuous GPS stations, seismic arrays, satellite imaging, and fiber optic sensing technologies provide a near real-time picture of subsurface processes. These tools have revealed a level of detail that was not available in previous decades, allowing for more precise tracking of changes as they occur. Despite this level of observation, the system retains elements of unpredictability. The timing of eruptions, the exact pathways of magma, and the localized effects of each event can vary, even within a well-monitored region. What can be established with confidence is the trend. The rift is widening, the volcanic system is active, and the interaction between these processes is intensifying in measurable ways. The landmass at the center of the North Atlantic continues to adjust under forces that operate on both geological and human timescales. Movement measured in millimeters per year accumulates into changes visible over years and decades. Episodes of rapid deformation compress these changes into weeks or even days, creating conditions that require constant monitoring and adaptation. As magma continues to accumulate beneath the Reykjanes Peninsula, the pattern that has defined recent years shows no indication of stabilizing. Instead, each cycle appears to reinforce the next, establishing a feedback system in which tectonic separation and volcanic intrusion accelerate one another. Ground deformation, recorded after the most recent eruptive phase, indicates that uplift resumed within weeks, not months, suggesting that the subsurface reservoir is being replenished at a sustained rate. Measurements show vertical displacement reaching several inches or multiple centimeters across monitored zones, a signal that pressure is rebuilding beneath the crust with consistency. The structure of the crust in this region plays a decisive role in how this energy is released. Iceland's crust is relatively thin compared to continental land masses, in some areas measuring less than 12 miles thick or under 20 kilometers. This reduced thickness allows magma to ascend more efficiently, shortening the time between accumulation and eruption. It also means that fractures can propagate more easily, enabling dikes to extend laterally across considerable distances. Some of the intrusions recorded in recent years have traveled several miles or multiple kilometers in a matter of hours, redistributing stress across a wide area before either erupting or stalling. This rapid propagation has direct implications for hazard zones. Traditional volcanic risk models often rely on relatively fixed exclusion areas based on known vent locations. However, the current activity demonstrates that new fissures can open beyond previously mapped zones, expanding the footprint of potential impact. In practical terms, this means that infrastructure considered outside high-risk boundaries can become exposed with limited advance warning. Roads, pipelines, and communication lines that cross the peninsula are particularly vulnerable due to their linear nature, intersecting multiple potential fracture paths. Thermal imaging and satellite observations have identified persistent heat anomalies even between eruptions, indicating that magma remains close to the surface across portions of the rift zone. These zones, measured at temperatures significantly above surrounding ground, suggest that the system is not fully resetting between events. Instead, it maintains a partially pressurized state, reducing the threshold required for subsequent eruptions. This condition aligns with the observed reduction in time intervals between eruptive episodes over the past several years. The accumulation rate of magma beneath Svartsengi has shown a degree of regularity, with volumes approaching approximately 17 million to 23 million cubic meters prior to each eruptive release. When translated into volumetric flow rates, this corresponds to the injection of hundreds of thousands of cubic meters per day during peak accumulation phases. In imperial terms, this equates to tens of millions of cubic feet of molten material entering the system daily. Such sustained input underscores the strength of the source feeding the system from below. Seismic data provides another layer of detail. Swarms of earthquakes precede each intrusion, often numbering in the thousands over short periods. These events are generally low in magnitude but high in frequency, reflecting the fracturing of rock as magma forces its way through existing weaknesses. The distribution of these quakes outlines the path of advancing dikes, allowing researchers to map subsurface movement with increasing precision. In several cases, the direction of seismic activity has shifted abruptly, indicating changes in pressure gradients that redirect magma flow. The relationship between seismicity and eruption timing has become more refined through repeated observation. A rapid escalation in earthquake frequency, combined with measurable ground uplift and gas emissions, typically precedes surface activity by a narrow window. However, not all sequences culminate in eruptions. Some intrusions dissipate their energy underground, leaving behind altered stress fields that can influence subsequent events. This partial predictability introduces both capability and limitation, enabling short-term alerts while maintaining uncertainty over final outcomes. Gas emissions remain a persistent concern. Sulfur dioxide levels recorded during recent eruptions have periodically exceeded health thresholds in nearby areas, prompting temporary evacuations and restrictions on outdoor activity. The dispersion of these gases depends on wind patterns, which can carry emissions across populated regions within hours. Monitoring stations track concentrations in real time, measuring parts per million to assess exposure risk. Even when eruptions subside, residual degassing from cooling lava fields can continue to affect air quality for extended periods. The economic dimension of this activity is measurable. Repeated evacuations of Grindavik have disrupted local industries, including fishing operations that rely on access to coastal infrastructure. Repair and reinforcement of damaged systems require continuous allocation of resources, while contingency planning for future events adds to operational costs. On a broader scale, the continuation of volcanic activity introduces variability into regional transportation networks, particularly aviation routes that may need to adjust in response to gas plumes or ash dispersion. Geospatial mapping of new lava fields indicates that recent eruptions have covered several square miles or multiple square kilometers, altering the surface topology of the peninsula. These flows, while typically slow-moving, can advance at rates of several yards per minute or a few meters per minute, depending on viscosity and slope. Barriers constructed to divert lava have demonstrated partial effectiveness, redirecting flows away from critical assets in some cases. However, their success is contingent on precise placement and the evolving behavior of each eruption. Hydrological systems are also affected. The emplacement of impermeable lava layers modifies groundwater pathways, potentially redirecting subsurface flow and altering the availability of water in certain areas. In addition, the interaction between hot lava and surface or subsurface water can generate steam explosions, adding another hazard component to eruptive events. These interactions are localized but can produce rapid, high-energy releases that extend the impact zone beyond the immediate lava flow. Over longer timescales, the continuation of rifting contributes to the gradual reconfiguration of Iceland's landscape. Valleys widen, new fissures develop, and existing geological features are displaced incrementally. While these changes are often subtle on a year-to-year basis, cumulative displacement over decades becomes measurable in feet and meters. Survey benchmarks installed across the peninsula have recorded horizontal shifts approaching several inches over relatively short observational periods, reinforcing the reality of continuous plate divergence. The interplay between deep mantle processes and surface expression remains a central focus of ongoing measurement. The mantle plume beneath Iceland supplies heat and material that sustain volcanic activity, while the separating plates create the space necessary for that material to ascend. Variations in plume intensity or composition could influence eruption size and frequency, though such changes operate on timescales that are more difficult to resolve with current data. What is observable is the consistency of supply in the present phase, supporting repeated cycles without significant interruption. Fiber optic sensing technology, deployed across a monitoring corridor approximately 62 miles long, has introduced a new level of resolution. By detecting minute temperature and strain changes along buried cables, this system effectively transforms existing infrastructure into a continuous sensor array. Data from this network has captured the passage of dikes in near real time, recording deformation as it propagates through the crust. This capability enhances situational awareness, providing early indication of intrusion events even before surface signs become visible. If you want more detailed, data-driven coverage on events like this, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.